Hi everyone, uh, my name is Haryana Thomas and I'm a PhD student at Dr. Fibrosis, and today I'm very excited to be sharing my research with you. We have some surprising, exciting results, and the title of my talk today is Modeling Cellular Signaling and Communication During Diabetic Kidney Disease. And so the motivation for our research is that chronic kidney disease is a significant health problem in the US. So 1 in 3 adults are at risk for chronic kidney disease. And 9 out of 10 of those who do develop CKD are undiagnosed, making chronic kidney disease the 9th leading cause of death in the US. And one of the major contributors of chronic kidney disease is diabetic kidney disease. And the reason for these numbers, for this significant health problem, is that diabetic kidney damage is a complex process, and we haven't developed treatment methods or diagnosis methods that are effective. And so we want to use computational and mathematical methods to understand these complexities of diabetic kidney damage so that we can develop better treatment methods and decrease these numbers. So what is happening within the kidney? So the glomerulus, which is the filtration unit of the kidney, is the center of this diabetic kidney damage. So the glomerulus is a sac-like structure which has these capillaries that branch and form within it, which allow the filtration of urine and other waste materials through it. And your kidney has thousands and thousands of these glomeruli. And they all function together to filter out all the waste from your blood. And if you take a cross-section of the glomerulus, this is kind of what you see with the capillaries here and the mesangial tissue, which acts as support to support these capillaries. And the mesangial cells maintain this tissue that's around it. And during diabetes, one of the hallmarks of glomerular damage is extracellular matrix accumulation. And the dysfunction that occurs within these cells causes the excess production of collagen, which leads to extracellular matrix accumulation. And so we want to study how this extracellular matrix accumulation affects function of the glomerulus. And so our aim is to develop a model to understand the dynamics of cellular communication within the glomerulus during diabetic kidney disease. So experiments have shown that these cells within the glomerulus, podocyte cell, endothelial, and mesangial cells, are in communication, and that their communication is very important. For example, the inhibition of VEGF signaling from endothelial cells affects mesangial cell migration and the formation of these mesangial tufts, which leads to glomerular failure. And so we know from experiments that these cells are in communication, and that cellular communication between these 3 cells is very important. And so we want to study how does this extracellular matrix accumulation, which is a hallmark of diabetic kidney disease, affects the ability of these cells to communicate. And we hypothesize that as the extracellular matrix accumulation within the mesangium increases, the ability of these cells to communicate will decrease, because this mesangial area is the medium through which the signals will travel to get to these other cells, and it's the medium through which these cells will communicate. And so as extracellular matrix accumulation increases, then their ability to communicate will decrease. That's what we hypothesize. And so one of the first thing we got to do is come up with a mathematical relation to describe how the transport property of the matrix changes with disease, because cellular communication within the mesangium or paracrine signaling occurs through diffusion. And the mathematical model that we used was a well-validated model that shows that describes the relationship between the diffusion coefficient and the volume fraction. And so here we have D naught is the free diffusion coefficient, and D is the diffusion coefficient through the fibers, and phi is showing the volume fraction of the fibers. So this is kind of an exponential decay relationship that that shows that as the volume fraction increases, the diffusion coefficient decreases. So the more fibers there are, then the ability of these molecules to traverse through this medium will decrease, because these fibers act as a hindrance for the propagation or movement of these molecules. And so our hypothesis that as the extracellular matrix accumulation increases, and the ability of cells the ability of cells to communicate will decrease, was based on this. And so after coming up with this mathematical relation, we then needed to find a mathematical model to show how this change in diffusion coefficient affects the ability of cells to communicate. So we needed to quantify the ability of cells to communicate. We need a property, and as we searched through the literature, came across this paper in the proceedings for the National Academy of Sciences that quantified this property, and the property that they quantified was the effective signaling distance, which is basically the farthest that a receiving cell can be from a secreting cell and still receive a strong enough signal in a timely manner. And so the way they came up with this quantity was to solve a radial diffusion equation. So here we have the change in concentration with time, and it's dependent on the concentration gradient as well as the diffusion coefficient. So this is a well-known equation, and the boundary conditions that were applied were that there is a constant secretion rate at the surface, or a flux at r equals rho, which is the cell surface, and that there is zero concentration at infinite distance away from the cell, which is reasonable and makes sense. And the solution for this problem is a product of a few important parameters and a function that is a function of the dimensionless distance and dimensionless time. And here, this solution, these key parameters are secretion rate, cell radius, and the diffusion coefficient. And they're able to come up with a mathematical description for the effective signaling distance, which depends on this key non-dimensional parameter, which is an agglomeration of the key parameters that we looked at. And so the effective signaling distance they define as half the maximum propagation distance. So if the secreting cell was allowed to secrete for an infinite amount of time, at infinite time the system would reach a steady state. with a concentration profile that doesn't change. And they define the effective signaling distance as half that maximum propagation distance. And that value is dependent on these key parameters that we talked about earlier, Km, which is the concentration at which the signal is strong enough to induce a response in the receiving cell, which makes sense because as Km increases, so that's a larger threshold concentration, the effective signaling distance would decrease. And a smaller Km value would give you a larger effective signaling distance. And it's also dependent on the secretion rate of signaling molecules. So the more a cell would secrete, the larger the propagation distance, and then importantly, the diffusion coefficient of the signaling molecules. So so that is how they quantify the effective signaling distance. So we wanted to use this property to study how the effect of extracellular matrix accumulation affects this ability of cells to communicate. And the results that we found is that the effect of fibrosis on the diffusion coefficient and the effective signaling distance. So here on the left we see a graph that shows the diffusion coefficient as a function of the volume fraction. See that as the volume fraction increases, the diffusion coefficient for the different size solute molecules decreases, which is what we expected. And here on the right we have a concentration profile for the different volume fractions, and what we see is surprising, which is that as the volume fraction increases, the effective signaling distance increases as well, which is opposite to our hypothesis, which is that as extracellular matrix accumulation increases, the ability of cells to communicate will decrease. And so we can see that more clearly here, where these circles are showing the range of signaling for the different cases. Red is showing the healthy case, and then orange is showing the diseased case, the range of signaling for the diseased case, and then green is the moderate case, and purple is a reference case showing the maximum propagation distance. And we can see that as the level of fibrosis, or the level of extracellular matrix accumulation increases, shown by the diseased case, see that the ability of cells to signal, or their range of signaling, increases. And this property is magnified even more for larger signaling molecules. And we see here that relative to the purple, which is the reference, the range of signaling for these larger solute molecules is even greater. So in conclusion, we have modeled the change in the transport properties of the matrix due to the fibrosis. Then we have quantified the ability of cells to communicate so that we can study the effect of fibrosis, or extracellular matrix accumulation, on the ability of cells to communicate. And we have a very surprising finding, which is that as fibrosis, or level of extracellular matrix accumulation, increases, the ability of cells to communicate, or their range of signaling, increases. And so we're very excited about that. And so the future, what we want to do is we want to incorporate other disease conditions within a diabetic glomerulus to see how these disease conditions impact the ability of cells to communicate within the mesangium. And these conditions of a diabetic glomerulus are increased proliferation of mesangial cells and increased secretion rates of these mesangial cells, as well as increased receptor sensitivity. And so we want to study how these disease conditions affect the ability of cells to communicate. I'd like to thank my advisor for being supportive, and like to thank NSF for the funding, as well as Oklahoma State University, which is a hosting institution. Thank you for your time, and if you have any questions, do ask.